Good evening, linear algebra students. It's my evening. Um, consider the vector space M2 by 2. We've seen it in class, but remember that it's the vector space of 2 by 2 matrices with usual addition and scalar multiplication, the one that we have been doing since the very beginning. We've explained in class that this is a vector space, and we would like to, for this particular M2 by 2, we would like to show that these matrices form a basis for V. Okay? And what we have to do is to check the two properties of a basis. So I will actually remind these two properties before we begin. So I'll do it in black. So reminder that E1, E2, E3, E4 is a basis if, and we had two conditions, okay? These are the same condition as what we have seen in Rn, okay? So the first condition being that it's linearly independent. Let's actually write it here, I think. Linearly independent. And condition number two is that the span of these matrices, so span of E1, hopefully I will have the space, E3, E4, turns out to be the exact M2 by 2. Okay, so I have to push the M2 by 2, unfortunately, a little bit below. But that's it. The span must be exactly V, right? So I will actually write V. So in other words, we have to prove 1 and 2. So let's begin with 1. Okay. What we want to prove is that so actually let's state what we want to show. We want to show that if C1 times a matrix like 0, 1, 1, 0, 0, 0 plus C2 times 0, 1, 0, 0 plus C3 times 0, 0, 1, 0 plus C4 times 0, 0, 0, 1 is equal the zero matrix. Okay? Then it forces C1 all the way up to C4 to be all 0. Are all zeros. Okay, so this is what we want to show. Okay? Now the idea is that, so if C1 plus C2 plus C3 plus C4. So actually, let's actually write that this equation is obviously going to give it's obviously going to give C1, C2, C3, C4. So in other words, if this linear combination is giving 0, oops, I messed up here. Like plus all the way up plus C4, like 0, 0, 0, 1 is equal to 0, 0, 0, 0. And then actually, let's write this again, like C1, C2, C3, C4 equals the matrix 0, 0, 0, 0. Then equating the entries, we get C1 is equal to 0. C2 is equal to 0. I'm gonna write it like as I'm equating the entries. C3 is equal to 0, and C4 is equal to 0. All right, so before I erase all of this, let's actually just review the proof one argument after the other. We want to show that this is true, but we know that this is valid. So if this is equal to 0, it forces C1, C2, C3, C4 to be equal to 0. So it means that 1 is verified. All right, now I'm going to erase this thing, and we're going to re-verify the property number 2. So so now we're going to write any matrix A, right? So if A is in V, which is M2 by 2, right? Then, or actually, let's put it this way. A is in V if and only if A is equal to some matrix like A11, A12, A21, and A22. Okay, and by matrix addition, we can actually write this as being like, let's actually go slow here, okay? So by matrix addition, we can write this as being A11, 0, 0, 0, then plus 0, A12, 0, 0. You guys are probably already seeing where I'm going. So 0, 0, A21, 0, and finally plus, so 0, 0, 0, A22. So this is by matrix addition. And by actually using scalar multiplication, now we have A11 times the matrix 1, 0, 0, 0, plus A12 times the matrix 0, 1, 0, 0, plus A21, then we have 0, 0, 1, 0, and finally plus A22, 0, 0, 0, 1. By the way, what we're like just to, we're showing number 2 here. Okay, and this is true for some numbers. So for some real numbers, A11, A12, A21, A22 in the real number set. Okay, so what does it mean? It means that A is in V. So let's actually rewrite this. A is in V if and only if A is a LC of E1, E2, E3, E4. And this means, of course, that A is in V if and only if A is in the span of these matrices, right? A is in the span of E1, E2, E3, E4. And this is enough to prove that V is equal to the span. So in other words, the conclusion is that we verified that E1, E2, E3, E4 is a generating set for V, right? The span of it is equal to V. So E1, E2, E3, E4, okay, is a generating set for V. Which means that the condition number 2, which is right here, is verified. So 2 is verified. Actually, I wrote a little bit too much. You could have just compared this with the number 2 that's written over here right away. All right. So now the full conclusion that we get from it, pairing 1 and 2 together, we see that it means that E1, E2, E3, E4 is a basis. Is a basis for V. There you go. And I'm even going to write QED at the top. All right, this is it. So just to let you know, guys, that in class you can pretty much assume that this is a basis for the vector space M2 by 2. Exactly like the standard basis of our n, which is like the standard basis of our tree, for example, would be like 1, 0, 0, 0, 1, 0, and 0, 0, 1. Well, the standard matrix, the standard basis of m by n would be all of these matrices for which you successively make 1 entry 1 and all the other zeros. Okay, so you can take that for granted. All right, I hope this was helpful. See you either in class or in the next video.